So we know that Newton's first law, the law of inertia, applies to objects that are at rest or objects that are in motion with a constant velocity, and our net force acting on these objects is zero. Otherwise, they would do something we call accelerate. Let's take a look at Newton's law. Before we begin, let's do a little bit of math review because we'll need this. And I want to take a look at proportionality and what is a directly proportional function versus an indirectly proportional function. Well, a directly proportional function, you recall, and by the way, this is our symbol for proportional. So what we would say for a directly proportional function, as you recall from math, we have y is directly proportional to x, and for an indirectly proportional function, y is proportional to 1 over x. They're inverses of each other. If we were to turn this into equality, we would have y equals our constant of proportionality, k, times x. And of course, if we were to graph this, this is a function that passes directly through our origin, straight line, with our slope being our constant of proportionality, k. If we were to take y equals kx, what would happen if we were to take our input, and instead of kx, what if we were to double it? What if we put a 2x in? So if we were to double our input, what would we have to do to our output to keep this balanced? If we were to put 2x in here, of course, our output would also double. All right. If we were to take a third of our input, and instead of putting x, put an x over 3 in here, what would happen? Well, we would end up getting a third of our output. And that's what directly proportional means. If we were to double our input, we'd double our output. If we were to quadruple our input, we'd quadruple our output. If we were to take input divided by 3, our output divides by 3. If we were to take our input and divide by 100, our output would divide by 100. Directly proportional. Indirectly proportional works a bit differently. Well, first of all, this function is a hyperbola. And it looks something like this in quadrants 1 and 3. If we were to use this as an equality, we'd have y equals k over x, where k would change the shape a bit in or out towards the origin, depending on the value of k. In the same sense, what would happen in this case if we were to take our input, x, and replace it, for example, to double it? What would happen with 2x? Well, we'd have k over 2x. Well, that means our y value would also have to be divided by 2. So if we double our input, we actually have our output. Our output is divided by 2. All right, so it's just the opposite of what happens with directly proportional. Doubling the input here, replacing x with 2x, halves our output. In the same sense, if we were to take our input and divide by 4, for example, what would happen to our output? Well, we would actually have to have 4 times our output. All right, and so if we were to quarter our input, it turns out quadrupling our output. So it's an inverse function. So Newton's second law. Typically, we'll talk about applying this to an object that's not in equilibrium. So our net forces are not zero, and therefore the object is accelerating. All right, and here's what Isaac Newton said. If you were to read his original writing, this famous work called Principia, he phrased it as such. He broke this down into 3 different ideas. He said, first of all, that the object's acceleration, which we call A, is directly proportional to the net force acting on the object. In other words, our acceleration is directly proportional to our sum of our forces. If we were to turn this into a mathematical equation, we would have A equals some sort of k times our sum of our forces. And remember, acceleration and force are both vector quantities. We have both a magnitude and a direction for those. He also made a note through experimentation that an object's acceleration is inversely proportional to the mass of the object. All right, and as you recall, our acceleration, if we return to the mathematics, would be k over m. We actually have our acceleration proportional to 2 things then. We've got directly proportional to the sum of the forces and indirectly proportional to the mass. Well, we can join these 2 concepts together into one equation. So we have acceleration is directly proportional to the force, so that goes to the numerator for our equation, and indirectly proportional to our mass, goes in the denominator. And if you think about our concept from the prior page, if we're directly proportional to the force, if we were to double the force on an object, what would happen to our acceleration? It would double. If we were to double the mass, because we're in the denominator, it would halve our acceleration. Oftentimes, we don't like to see fractions in math, so we'd actually multiply both sides by m. And so we might rewrite the equation like this. And typically, this is the way I do write it. The sum of the forces equals mass times acceleration. Now, Newton came up with a third idea as well related to this. And if you take a look at this equation, on the left side of our equation, we've got force as a vector. On the right side of the equation, we have acceleration as a vector. Mass, of course, has no direction associated with it, so that's just a scalar quantity. And if you recall, we did a little example when we were learning about vectors. If we had a vector A, and I asked you, what's 2 times A? Well, 2 times A is just a vector that's twice as long. In the same sense here, if I have some vector A, multiplying it by a mass, which is a scalar quantity, if our mass happens to be 2, I'll get my acceleration. The vector is twice as long, and we call that a force. If mass is a half, it's just going to have the size of the acceleration vector and give us our force that's half as long. And what's important here, because this is a vector, multiplying it by a scalar does not change the direction at all. And so Newton's third idea associated with this, our acceleration is in the same exact direction as the net force. In other words, if we have our acceleration vector, when we multiply this by our mass scalar quantity, it will just change the length of our force vector, but it won't change the direction. So acceleration times mass gives us our force. Direction's got to be the same. And you need to know each of these 3 items on our next quiz. So let's use dimensional analysis to figure out what the units are for force. So let's look at MKS units. And all I'm going to do to figure out dimensional analysis, really all we need to do is plug in units into our equations and see what we get. We need to plug in units for mass and units for acceleration. So if you look at this, our mass units are kilograms, and our acceleration units are meters per second squared. So force units are just kilograms times meters per second squared. We actually call 1 kilogram meter per second squared, we actually call that 1 Newton. Of course, honoring Sir Isaac Newton, who came up with this idea. And in terms of US units, force units are pound. We tend to prefer to do work in metric units because they're a lot easier to work with. And the big reason is because we don't really have nice mass units to work with in US units. Slugs are not nearly as easy to use as kilograms are. So one of the things that you should do on your own right here, I want you to figure out using the fact that you know a kilogram times meters per second squared is a Newton. And we know something about pounds. We know from our conversion factors pounds to kilograms. I want you to figure out how many newtons would be in a pound. Do a conversion and figure that out for me. The weight of an object we talked about before depends on 2 things. It depends on the mass of the object and how strong the gravitational pull is on that object. You'll notice we have mass, which fits into our equation above, right there. And we have our acceleration, which is going to fit right there. So we're going to plug these in so we can actually use Newton's second law to calculate weight. Weight is simply equivalent to force due to gravity, and all you have to do is take your mass and we would multiply it by acceleration due to gravity. Now you'll notice here, if I want to do this using a vector quantity, I have to insert my own sign here because g is the absolute value. It's only the magnitude of gravitational acceleration. We'd put a negative in to indicate it's moving downward. Weight is just a force, and in fact, it's the force due to gravity. And so you want to keep in mind, and this is something everybody mixes up for some reason, and I'm going to say this 100 times, so please don't mix this up. Weight is simply force due to gravity. These 2 ideas are the same. Weight and force due to gravity are synonymous. If I say weight, I mean force due to gravity. If I say force due to gravity, I mean weight. And to calculate your weight, it's easy. Just multiply your mass of the object times gravity. So we can use the equation above to find our force due to gravity given our mass, or given a mass, we can find the force due to gravity. All right, so this is a reversible process. And let's do a couple of examples. And to make our math easy, I will use either g is approximately 10 meters per second squared or 32 feet per second squared. But remember, because I don't have mass units and US units that are easy to use, you generally speaking won't see me use this 32 feet per second squared quantity. Another key idea to keep in mind is on Earth, I should have put a star next to this, on Earth 1 kilogram is equal to 2.20 pounds. So we can use that as well to help us along. So let's go ahead and answer question number 1. How much does an 8 kilogram object weigh on Earth? And how about on the moon? Let's find this in MKS units and US units. So I'm trying to figure out the weight of an object. Well, our weight equals our force due to gravity equals whatever our mass of the object is times our acceleration due to gravity. All right, well, we're given 8 kilograms is our mass, and I'm going to multiply by gravity. Our gravitational acceleration is 10 meters per second squared. So I get 80 kilogram meters per second squared. Of course, rather than writing that gobbledygook here, I can just call that 80 newtons. All right, there's my answer. So there's my weight, which is also known as my force due to gravity. Same thing. All right. What if instead of metric units, what if I wanted to find US units? Well, there's a quick way to do this. But remember, on Earth, we also have another little factoid that we can use. We know that we can go from kilograms to pounds directly, because we know that 1 kilogram equals 2.20 pounds. So 80 newtons is equivalent to 17.6 pounds, roughly speaking. Our 80 newtons here includes a little bit of rounding error, because we should actually, if we want to be more exact, use 9.8 meters per second squared. Our 1 kilogram equals 2.20 pounds is accurate to 3 decimal places, though. All right, so that is on Earth. What about on the moon? How do we find these weights on the moon? Well, there's an easy way to do this. If we were to reduce our gravitational pull by half, what should happen to our weight? It should divide by half. It turns out that on the moon, we're about 1/6 the gravitational pull. So if you remember that little fact, we can just divide these numbers by 6, and you'll come up with a number. So I can just divide this number by 6, and I'll come up with a new number. So you can go ahead and do that. So that's just a quick little fact you might want to remember about Earth's gravitational pull compared to the moon. And remember, the Earth's gravitational pull is stronger than the moon's because the Earth has a lot more mass. So let's take a look at example number 2. An object weighs 200 newtons. All right, so its weight is 200 newtons. Find its mass. By the way, its weight also is its force due to gravity. Same thing. All right, let's write down our equation. Force due to gravity, or weight, equals mass times gravity. I'm actually given our force due to gravity, so I'll plug that in the left side. And our mass is what I'm trying to find. That's our unknown. And our gravitational pull is 10 meters per second squared. All right, divide both sides by 10, and I'm going to get my mass equals 200 newtons over 10 meters per second squared. Now I've got a little bit of problem because I don't know how to cancel newtons and meters per second squared. Or do I? So let's find the force due to gravity acting on an object that weighs 100 pounds. All right, so we have an object that weighs 100 pounds. The question is, how do we find the force due to gravity? Hello, folks, that is the force due to gravity. So don't forget, weight and force due to gravity are synonymous. So if I give you the weight, you also know the force due to gravity. Now, we might want to find that weight in newtons, so we've got to do a little bit of work to get that. They also ask us to find the mass. So let's find the mass first. So I'm going to take 100 pounds. How do you calculate mass? Well, remember, we're here on Earth, so let's use our conversion factor to do this. So I have 100 pounds times, there's 2.20 pounds per kilogram. And if you calculate this, I get 45.4545 repeating. So I'll just round this to 45.5 kilograms. All right, there's our mass. We didn't even need to use Newton's second law to do this. All right. Now, if we did want to find our weight in newtons, we can do that now that we have a mass. So I'm just going to use weight equals force due to gravity equals mass times gravity. We can just take our mass, which is 45.5 kilograms, and we'll multiply that by our gravitational acceleration, which is about 10 meters per second squared rounded. And we're going to get about 455 newtons.